For the first few days of life, an embryo is basically just doing math.
Right.
I mean, one cell becomes two, two becomes four, four becomes eight. It's just addition or multiplication, really.
Exactly, yeah. It is fundamentally an exercise in cellular replication.
Under the microscope, it's essentially this exercise in geometry, just dividing and counting in a highly predictable rhythm.
It is. At that early stage, it's binary, and in many ways, it's a very quiet internal process. We're just watching the numbers climb.
But then something completely shifts. The math stops being just math and it turns into architecture.
Oh, that's a great way to put it.
Yeah, the embryo doesn't just divide anymore, it builds. It actively decides to become something with a shape, with a purpose, with an inside and an outside. It is like watching a pile of bricks suddenly decide to, assemble themselves into a house.
That is exactly it. And that shift, that sudden leap from a simple cluster of cells to a complex, organized structure is the absolute definition of a developmental revelation.
A revelation, yeah.
Yeah. It's the moment the embryo declares its structural competence to the lab, to the clinicians, and ultimately to you, the patient.
So welcome to our 10th deep dive into the IVF lab. And today, we're looking at the exact moment that architectural blueprint goes live.
Right.
If you've been following along with us, you'll remember where we left you last time. We were peering through the microscope at cleavage stage embryos on days 2 and 3 of their development.
Yes, exactly.
We were counting those individual cells, the blastomeres, looking at their symmetry, checking for fragmentation, and trying to gauge their early developmental momentum.
Right, looking for those early signs of health.
But today, we're exploring what happens next. We're going to unpack exactly how that chaotic cluster of cells somehow learns to compact itself.
It's a huge transition.
It is. We're going to look at how it carves out a fluid-filled cavity from nothing, and how it miraculously separates into two entirely distinct cellular populations.
And we really need to take this slowly because for you listening, reaching the blastocyst stage is not just another day in the lab.
No, not at all.
Before this point, the embryo has been relying almost entirely on the maternal energy and the genetic instructions that were packed into the original egg.
The oocyte.
Yes, the oocyte. Before fertilization even occurred, back when it was maturing from the M1 to the M2 stage, it was hoarding these supplies.
Right.
But to become a blastocyst, the embryo has to turn on its own genome. It has to start directing its own survival.
Which is a massive shift in responsibility.
Absolutely. When we see a blastocyst form, it shifts the entire clinical decision-making process. It changes how we think about transfer, freezing, and what we can learn about the embryo's future.
So let's start with the sheer weight of this developmental stage.
Yeah.
Why is reaching the blastocyst stage such a monumental hurdle?
Wow.
Why do we see so many embryos simply stop growing between day 3 and day 5?
To understand the weight of this stage, you really have to understand a biological event called the maternal zygotic transition. Like I mentioned, when an oocyte is developing in the ovary, it packs itself full of messenger RNA and proteins. For the first 3 days after fertilization, the embryo is basically coasting on those maternal supplies.
Right, it's just riding the wave.
Exactly. It doesn't really need to read its own DNA yet. But right around day 3, usually when the embryo reaches the 8-cell stage, those maternal supplies run out.
Oh.
Yeah. The embryo must activate its own genome. It has to start reading its own genetic code and producing its own proteins to survive.
So it has to switch from battery power to, generating its own electricity.
Yes, that's a perfect analogy. And that switch is incredibly precarious. If there is a major error in the embryo's genetic code, it just starts.
The power goes out.
Right. Or if the cellular machinery fails to boot up properly, the embryo will simply arrest. It will stop dividing completely.
Wow.
This is why the transition from day 3 to day 5 is a major attrition point. It is a natural biological filter.
A filter, okay.
Yeah, so we might have 8 beautiful embryos on day 3, all looking perfect, but only 4 of them might actually possess the intact DNA required to make the leap to blastocyst.
Man, imagine sitting by your phone on day 5. Every time it rings, your heart stops because the embryologist is looking through the microscope right now.
This is terrifying for patients.
It really is. They're looking for that architecture.
Yeah.
And when they tell you that out of your 8 embryos on day 3, only 4 made it to blastocyst, the initial reaction is almost always grief.
Of course. It feels like a massive loss.
It feels like you lost half your cohort. But, isn't this filtering actually giving us crucial information?
It absolutely is giving us indispensable information. I try to remind patients of this constantly.
Because we transferred all 8.
Right. If we transferred all 8 of those day 3 embryos, We would be transferring 4 embryos that simply did not possess the biological machinery to continue developing.
They were never going to make it anyway.
Exactly. The laboratory environment didn't break them. It simply provided a space for them to reveal their innate potential.
That's a huge paradigm shift for how you look at it.
Reaching the blastocyst stage is the clearest proof we have that an embryo has sustained development through those early vulnerabilities. It proves the embryo's DNA is actively working.
Orchestrating all those incredibly complex tasks.
Precisely.
That brings me back to the architecture analogy. In those early days, the cells are just dividing. It's like a construction site where delivery trucks are just dropping off thousands of bricks.
Yes, just piling them up.
Right. You look at the pile on day 3 and say, wow, that's a lot of bricks. This is going to be a great house.
But a pile of bricks is not a house.
Exactly. The blastocyst stage is when those bricks are finally mortared together. You finally step back and see the walls, the rooms, the roof.
Yes, and that is why this architectural structure dictates everything we do next in the clinic.
Because you finally have something solid to work with.
Right. This is the stage where decisions are finalized regarding embryo transfer. It is the stage where we can confidently perform cryopreservation, freezing the embryos for future use. And perhaps most significantly in modern IVF, it is the only stage where we can safely perform a biopsy for pre-implantation genetic testing, or PGT.
Right, because before this stage, there just isn't enough architecture to safely take anything away.
Exactly.
You can't take a blick out of a loose pile of 8 bricks without compromising the whole stack. But once you have a massive structured house, you can carefully sample a shingle from the roof.
That is a very accurate way to visualize it.
So if we need that solid house, how do the bricks actually start coming together? Let's step into the shoes of the embryologist on day 4.
Okay, day 4.
The embryo is no longer just a loose cluster of individual round cells. It enters a stage called compaction.
Yes, compaction.
What does this physical transition actually look like to you?
Well, if you were to look through the oculars of the microscope on day 4, you would see a very subtle but beautiful transformation. Subtler than the early divisions?
Much subtler. Up until now, the cells, the blastomeres, have looked like a cluster of individual grapes. You can clearly see the distinct curved border of every single cell.
Like little bubbles pressed together.
Right. But during compaction, those cell borders begin to blur. They become completely indistinct.
Oh, wow.
The cells start to flatten against one another, really maximizing their contact area. The embryo shifts from looking like a cluster of grapes into a smooth, solid, cohesive mass.
And there's a specific name for this mass, right?
Yes, that mass is called a morula. It comes from the Latin word for mulberry because of its tightly packed appearance.
A mulberry. It looks like they're just, melting into each other. But I assume there's some intense molecular mechanics happening beneath the surface, right?
Oh, absolutely.
How do they actually stick together like that?
It is a highly active, incredibly organized process. As the embryo reaches this stage, the cells begin expressing a specific protein called E-cadherin on their surfaces.
E-cadherin.
Okay.
Yes. And E-cadherin is essentially a molecular zipper. It requires calcium to function, which is present in the surrounding fluid in the culture dish.
Right. From a media.
Exactly.
Yeah.
And it binds the outer membranes of adjacent cells together with incredible force. They are literally zipping themselves together, forming what we call tight junctions.
Tight junctions, so they're sealing themselves off.
Yes. This seals off the inside of the embryo from the outside environment completely.
I love the idea of them zipping together. To me, compaction feels like a sports team right before a major game-defining play.
Okay, I like where this is going.
During the first half of the game, the players are spread out all over the field doing their individual jobs. That's the cleavage stage.
Right, the early math.
Yeah. But then the whistle blows, and they all run into the center and form a tight, completely unified huddle. You can't tell where one player ends and the other begins.
They are just one solid unit of focus.
Exactly.
Yes, and just like a huddle, that physical proximity completely changes how they communicate with each other.
Because they're actually touching now.
More than touching. By zipping together so tightly, the cells establish gap junctions. These are microscopic channels that allow them to pass chemical signals directly from the cytoplasm of one cell to the cytoplasm of another.
Oh, wow. So they're physically sharing their internal fluid.
Yes. They are sharing information and preparing for the heavy lifting of the next stage. The outer cells have to coordinate with the inner cells.
So they're literally talking to each other through these channels.
Exactly. Without this compaction, without this specific communication, the embryo simply cannot form the complex structures required for implantation later on.
Okay, so a beautiful, tightly compacted morula shows us that the embryo has forward momentum.
It does.
But let me push back on this for a second. If the morula is this highly organized, beautifully zipped together structure, why don't embryologists just grade and transfer at the morula stage?
That's a very common question.
Because why wait for day 5 if they already look so good on day fair?
Because the morula is still just the preparation. It's the bridge, but it is not the destination.
Oh, okay.
While a compacting morula is a great sign, years of observation have taught us that not all morulae successfully make the next jump.
Really? They could just stop after all that work?
Unfortunately, yes. An embryo can compact beautifully, look like a perfect morula on day 4, and then suddenly arrest. The DNA might fail to initiate the next sequence of instructions.
Wow, so the huddle breaks apart.
Or it just stays a huddle forever. If we transferred at the morula stage, we would be transferring a significant number of embryos that were destined to fail just hours later.
That makes total sense.
We wait because the true test of the embryo's competence happens when that solid structure finally opens up from the inside.
Right, so the team is huddled, they have their play, now they have to execute it.
Exactly.
And the execution of that play is what we call cavitation. How exactly does a solid ball of tightly zipped cells suddenly become a fluid-filled balloon?
Cavitation is the biological process where the embryo literally carves out a space for its future.
Carves it out.
Yes. Remember those tight junctions we just talked about?
Yeah.
The cells on the outside of the morula have zipped themselves together so tightly that they have created a waterproof seal.
Right, the ecadherin zippers.
Exactly. Once that waterproof seal is formed, those outer cells activate microscopic pumps on their internal membranes.
Pumps.
Yeah.
Like literal mechanical pumps.
Molecular pumps, yes. Specifically, they use sodium-potassium ATPase pumps. These pumps actively push sodium ions from the outside environment into the microscopic spaces in the center of the solid morula.
Oh, wow. And I remember from high school biology where sodium goes, water has to follow.
Exactly. You've got it. Through the rules of osmosis, fluid is drawn through specialized water channels called aquaporins.
Aquaporins.
Right. And that water floods into the center of the embryo to dilute that concentrated sodium.
Because nature hates an imbalance.
Precisely. As the fluid accumulates, it begins to push the internal cells apart. It creates a tiny pocket of fluid.
So it's forcing its way in.
Yes. And over a matter of hours, that tiny pocket grows and expands until it forms a massive internal cavity.
And that cavity has a name, right?
Yes. That fluid-filled cavity is called the blastocyst. And the moment that cavity begins to form, the embryo officially becomes a blastocyst.
So if we're watching this under the microscope, what does it actually look like?
At the very beginning, an early blastocyst might just have a tiny crescent-shaped sliver of fluid visible between the compacted cells.
Crescent shape.
Yeah, it looks almost like a little crack of light inside a dark stone. But as the pumps keep working, that fluid pocket grows. The cavity begins to dominate the internal structure.
It's just filling up and pushing everything else out of the way.
It physically pushes a specific group of cells to one side while stretching the rest of the cells incredibly thin around the perimeter to contain the expanding fluid.
It sounds almost violent at a microscopic level.
It is a massive physical overhaul.
But I want to make sure I understand the mechanics of this fluid pumping. Is this just passive? Or is this an active, energy-intensive biological process?
Oh, it is entirely active, and it is incredibly energy-intensive.
Okay, so it takes work.
A lot of work. Pumping those sodium ions against a concentration gradient requires massive amounts of ATP, which is the cellular currency of energy.
Right, the energy molecules.
The embryo's mitochondria are working furiously, burning through fuel to power those microscopic pumps. Cavitation proves the embryo's metabolic strength.
So if it can't cavitate, it means its engine is broken.
Exactly. It proves that its cellular machinery is functioning at a highly sophisticated level.
It is actively inflating itself. It's building pressure from the inside out. But, as we know from basic physics, as the fluid fills, the embryo cannot stay the same size forever.
No, it can't.
You can only pump so much air into a tire before the tire itself has to stretch. And that brings us to the next profound phase of development, which is expansion.
Expansion is one of the most dynamic phases to observe in the lab.
I bet.
The embryo is still encased within the zona pellucida, which, as you know, is the protective protein shell that surrounded the original oocyte.
All right, the shell is still there from day one.
Yes. But as the fluid cavity enlarges, the internal hydrostatic pressure builds. This pressure forces the entire blastocyst to expand outward, pressing against that outer shell.
Let's walk the listener through the distinct stages of this expansion, because this is a massive part of what the embryologists are grading on those lab reports, right?
It is a huge part of the grade. First, we have the early blastocyst, where the cavity is small, occupying less than half the volume of the embryo.
Just a little crack of fluid.
Right. Then we move to the expanding blastocyst. Here, the cavity has grown significantly, occupying more than half the volume, but the overall size of the embryo hasn't changed much yet.
It's just filling the available space inside the shell.
Exactly. But then it hits a critical point.
Okay, what happens then?
The cavity continues to swell, and we reach the expanded blastocyst stage. At this point, the blastocyst is physically growing larger.
So the whole thing is actually increasing in diameter.
Yes, the internal pressure is so great that it is pushing outward against the zona pellucida, causing that protective shell to stretch and become visibly thinner.
I always picture the zona pellucida like a tailored suit.
A tailored suit, I like that.
Yeah, I mean, when the embryo was just a few cells, the suit fit perfectly. It kept everything contained. But now, the embryo has grown so much, it has built this massive internal cavity, and the suit is getting incredibly tight.
Very
The
tight.
seams are stretching, the fabric is thinning out.
Yes, and when the suit stretches to its absolute limit, the embryo realizes it needs to break free. It cannot implant into the uterus while still wearing that shell.
Right, it has to touch the uterine lining directly.
The pressure becomes immense, but pressure alone isn't always enough to break the zona pellucida.
Oh, really? I thought it just sort of popped.
No, because the zona is made of tough, interlocking glycoproteins called ZP1, ZP2, and ZP3. It's very durable.
So how does it get out?
The embryo actively produces specific enzymes, proteases, that chemically dissolve a small hole in the stretched shell. This leads to the hatching blastocyst stage.
It literally digests its own way out.
Exactly. Under the microscope, you can see a breach in the zona pellucida, and the embryo begins squeezing its cells out through that tiny hole.
Squeezing through.
Yeah, it looks almost like a figure eight. The fluid cavity deflates slightly to allow it to squeeze through, and then re-expands on the other side.
That is wild.
And finally, we have the hatched blastocyst, where the entire embryo is completely free of the shell, floating in the culture media, ready to implant.
It's bursting at the seams to prepare for implantation. But, if expansion is this dramatic and it ends with the embryo breaking free to implant, isn't a massive hatching embryo the ultimate goal?
That's what a lot of people assume.
Right. I mean, size must be everything at this stage.
You would think so, but here's where we need to introduce a heavy dose of nuance.
Okay, lay it on me.
Expansion tells us about structural progress. It tells us that the pumps are working, the mitochondria are generating ATP, and the cavity is forming.
Which are all good things.
Yes, very good things. But an embryo can be fully expanded and still be of poor biological quality. Expansion only tells us how big the house is getting.
Right.
It does not tell us who is living inside the house. The true biological potential of the embryo lies in the actual cells themselves.
The size of the house versus the inhabitants. That completely shifts how we look at this.
It's a crucial distinction.
We need to look past the fluid, past the expansion, and look at the cells. And that brings us to the very heart of the blastocyst stage. Because up until the morula stage, all the cells were basically the same, right?
Correct.
They were all just general-purpose blastomeres.
They were considered totipotent, meaning any one of those cells had the potential to become absolutely any part of the fetus or the placenta.
They were blank slates.
Exactly. But during cavitation, a permanent, irreversible divergence occurs. The cells differentiate into two completely distinct lineages. Two distinct destinies.
And what are those?
They become the inner cell mass, which we call the ICM, and the trophectoderm, which we call the TE.
How does a cell know which destiny to choose? If they are all identical in the morula, what triggers half of them to become one thing and half of them to become another?
It is largely about physical position.
Really? Just where they happen to be?
Yes. The cells that end up trapped on the inside of the compacted morula experience a completely different microenvironment than the cells on the outside.
Because the outer cells are exposed to the fluid.
Right. While the inner cells are surrounded only by other cells, this physical positioning triggers different transcription factors.
So the environment changes their genetics.
It changes their gene expression. The inner cells start expressing a protein called OCT4, locking them into becoming the inner cell mass. The outer cells start expressing a protein called CDX2, locking them into becoming the trophectoderm. It is the very first cell-fate decision in human development.
That's incredible.
Yeah.
Let's break these two destinies down. Let's start with the inner cell mass. What is it, and what is its destiny?
Well, the inner cell mass is a cluster of cells located on the inside of the expanded blastocyst cavity.
Okay.
When you look at a blastocyst, the fluid cavity takes up most of the space, but tucked away on one side, clinging to the inner wall, is this dense grouping of cells.
Kind of like a little moon orbiting inside a planet.
Yes. And its destiny is nothing less than awe-inspiring. The inner cell mass is the group of cells that will go on to become the actual fetus.
The baby.
Exactly. Every single cell in your body, my body, your heart, your brain, your bones, originated from that one tiny cluster of cells.
That is staggering, just sitting there on the edge of a microscopic fluid bubble.
It really is.
When an embryologist looks at the ICM, what are they looking for to determine if it's healthy?
We are looking for a clear, distinct, and highly cohesive cluster. We want to see a multitude of cells packed tightly together.
So a lot of cells, very tight.
Right. A strong ICM looks robust, bright, and prominent. If the ICM looks sparse, if the cells seem loosely connected, or if it is difficult to distinguish from the surrounding cells, that raises serious concerns about its developmental potential.
Okay, so the ICM is the future baby. Now what about the rest of the cells? The ones that expressed CDX2 and were stretched thin to make the fluid cavity?
Those outer cells make up the trophectoderm, or TE. While the ICM is clumped together on the inside, the TE forms a single, continuous, balloon-like layer entirely surrounding the cavity and the ICM.
So it's the actual wall of the balloon.
Yes. And while the TE does not become the baby, its destiny is equally critical. The trophectoderm is destined to become the placental tissue and the supportive membranes.
The placenta.
It is the ultimate life support system.
So when the embryo hatches and attempts to implant, it's the TE cells that actually make physical contact with the uterine lining.
Exactly. They are the cells that dig in, establish a blood supply, and create the environment in which the ICM can thrive.
So they do all the heavy lifting for implantation.
They really do. When we assess the TE, we are looking for a continuous, highly cohesive epithelial layer. We want to see many, many cells tightly joined together, forming a sturdy outer wall.
I'm thinking of this entire structure like a complex space mission with a singular goal: safe arrival in a hostile environment.
I love space analogies.
The inner cell mass is the astronaut. It's the most precious cargo tucked safely inside the command module.
Right.
And the trophectoderm, on the other hand, is the rocket, the navigation system, and the heat shield all rolled into one.
That is perfectly said.
The TE is what allows the astronaut to survive the journey and successfully land on the surface of the moon, which in this case is the uterine lining. You need the astronaut to be healthy, but if the heat shield fails during re-entry, the mission is over, no matter how brilliant the astronaut is.
Yes, absolutely. And just like a heat shield, if the trophectoderm has a tiny crack in it, or if it is too thin, the entire structure is vulnerable.
It'll just burn up.
Exactly. The interplay between the two is absolutely critical. And to add another layer to your heat shield analogy, because the TE is on the outside, and because it is destined to become placenta rather than the fetus itself, the trophectoderm is the exact tissue that embryologists sample when they perform a PGT biopsy.
Right, because you don't want to touch the astronaut.
Never touch the astronaut.
So if you want to test the genetics of the embryo without harming the future fetus, you carefully remove a few cells from that outer TE layer. You are taking a tiny piece of the heat shield to test the integrity of the whole ship.
Exactly. We use a microscopic laser to gently separate 3 to 5 cells from the trophectoderm.
Just a tiny scrape.
Right. Because those cells originated from the same initial fertilized egg as the inner cell mass, their DNA is almost always a perfect match for the DNA of the future fetus.
It's a brilliant biological loophole that allows us to peek into the embryo's genetics safely.
It completely changed the field of IVF.
But that raises a fascinating question. Since these are two distinct cell lineages with two different destinies driven by different transcription factors, can they develop at different rates?
Yes.
Can you have a brilliant, robust astronaut, but a weak, failing heat shield? Or vice versa?
You absolutely can.
Really? So they aren't always matched in quality?
Not always. You can have discrepancies between the two lineages. You can see a blastocyst with a beautifully tight, prominent inner cell mass, but a sparse, disorganized trophectoderm.
Oh, wow.
Or you can see a strong, multicellular trophectoderm enclosing a tiny, barely there ICM.
So how on earth does an embryologist write that down on a medical report for a doctor to understand?
That is exactly what the grading system is for. The way we communicate this delicate balance is through a specific cipher.
Ah, the famous, or perhaps infamous, 3AA, 4AB cipher.
Yes, the letters and numbers that keep patients awake at night.
If you've ever received an embryology report, you've stared at these numbers and letters, trying to read the tea leaves. Let's methodically demystify this. How does the Gardner grading system actually work?
Let's take a typical grade, like a 4AB. This grade is composed of 3 distinct parts, evaluating the 3 major components we just discussed: expansion, the ICM, and the TB.
Okay, break it down for us.
The number at the front, the 4 form, describes the degree of expansion. This typically ranges from 1 to 6.
And 1 is the smallest.
Right. A 1 or 2 is an early blastocyst with a small cavity. A 3 is a full blastocyst where the cavity fills the embryo, but it hasn't started stretching the shell yet.
Still in the perfectly fitted suit.
Exactly. A 4 means it is expanded. The cavity is large and the zona pellucida is stretched thin. A 5 fort means it has started hatching out of the shell, and a 6 fort means it has completely hatched.
So a 4 simply tells us this embryo is fully expanded and stretched thin, ready to start hatching soon.
Correct.
Got it. The number is just the physical size of the house and the status of the shell. Now, what about the 2 letters that follow?
The first letter always describes the quality of the inner cell mass. The astronaut.
Okay, the first letter is the astronaut.
We typically use a grading scale of A, B, or C. An A grade means the ICM is excellent. It is tightly packed with many distinct cells.
The best case scenario.
Right. A B grade means it is still good, but perhaps slightly looser or with fewer cells than an A. A C grade indicates a poor ICM with very few cells, or cells that are disorganized and difficult to clearly identify.
So in our 4AB example, the A tells us the embryo has a top-quality, robust inner cell mass.
Exactly.
And the second letter, the B in 4AB.
The second letter describes the quality of the trophectoderm, the heat shield, again, graded A, B, or C.
So it's the exact same scale.
Yes. An ATE means there are many cells forming a cohesive, continuous, highly organized layer. ABTE means there are fewer cells, perhaps they are slightly uneven or less tightly joined.
Izzy.
A CTE means the layer is sparse with very few cells or large gaps in the cellular wall.
That sounds dangerous for a heat shield.
It is. So the B in our example tells us the outer layer is good, but perhaps not quite as perfectly uniform as an A-grade layer.
So a 4AB is an expanded blastocyst with a perfect astronaut and a pretty good heat shield.
That's a perfect summary.
But I have to push back here. You're describing this so cleanly, so clinically, but as an outsider looking in, this sounds almost like grading an art project.
I can see how it sounds that way.
You're looking at something microscopic, deciding if it looks tightly packed or slightly loose. Is there a massive risk of subjectivity here?
It's a fair point.
I mean, if I make my 4AB embryo, which I've been celebrating, and I move it to another clinic down the street, are they going to look at it and call it a 4BB or a 3BC?
That is a very fair and important question. Yes, there is an inherent element of subjectivity because we are relying on the human eye. It is a visual assessment.
So it's not like measuring a blood pressure.
No, it's not. But we work incredibly hard to mitigate that. Embryologists undergo rigorous, continuous training. We perform proficiency testing where multiple embryologists grade the same images blindly to ensure we are all aligned.
So there's quality control.
Massive quality control. And increasingly, clinics are using artificial intelligence software that analyzes the pixels of the embryo image to provide a standardized, objective grade.
Taking the human eye out of it entirely.
Exactly. That said, different clinics might have a slightly stricter human threshold for what constitutes an A versus a B.
So a 4AB in Clinic X might indeed be a 4BB in Clinic Y.
It is possible, yes. But here's what I want you, the listener, to take away. The core principle is consistency within the individual clinic.
As long as they're consistent with themselves.
Right. The grading system is not magic. It is not a definitive statement of the embryo's absolute potential. It is simply a structured tool that allows the laboratory to rank a cohort of embryos.
Just a ranking.
It allows us to say, based on physical appearance, this embryo looks slightly more robust than that one, so we should transfer this one first. The letters and numbers are a shorthand description of morphology, nothing more.
That is a crucial distinction. It's a ranking tool based on appearance. But as we know, appearance isn't everything.
Not at all.
Grading tells us what the embryo looks like right now at the exact moment the embryologist glances through the microscope. But an equally important factor, and one that causes endless confusion and stress for patients, is the clock.
Yes, the timing.
When did the embryo actually reach this beautiful 4AB stage? Because that brings us to the profound clinical significance of days 5, 6, and 7.
This is one of the most complex and frequently misunderstood aspects of IVF. We don't just assess the final structure, we assess the developmental kinetics.
Kinetics meaning speed.
Right. We assess the speed at which the embryo managed to execute this incredible transformation. Biologically, a day 5 blastocyst represents an embryo that has progressed through pre-implantation development at an optimal, efficient pace.
It hit all its marks right on time.
Exactly. It didn't rush, but it didn't lag. It hit all its developmental milestones, cleavage, compaction, cavitation, right on schedule.
So it's the gold standard.
When we see a high-quality blastocyst on day 5, it reflects highly efficient internal kinetics. Statistically, day 5 blastocysts with strong morphology yield the highest implantation rates. Therefore, they are usually prioritized.
Okay, so day 5 is the star pupil who finishes the test early and gets an A. But what about day 6?
Let's talk about day 6.
I know for a fact that many listeners have received the call saying, none of your embryos are ready on day 5. We are going to give them another day. And my God, the panic that's
It'll be awful. They feel like they failed.
Exactly. The feeling that the embryos are slow, that they are failing. Let's talk about day 6 carefully.
I want to be as clear and reassuring as possible here. Day 6 blastocysts are incredibly common in routine IVF practice.
Incredibly common.
Yes. They are highly valuable, and they result in thousands upon thousands of healthy babies every year. Slightly later timing does not automatically mean poor potential.
Really?
Embryo development is not a uniform machine. It is biology. Some embryos simply have a slightly different metabolic clock.
Let's use an analogy here. Let's think about baking a cake.
Right.
If you have 2 identical cake batters and you put one in an oven running at 350 degrees and the other in an oven running at slightly lower temperature, the first cake might be perfectly baked in 50 minutes.
Right.
The second cake might take 60 minutes. But once they're both fully baked, you pull them out and they are both structurally sound. They are equally delicious. The extra 10 minutes didn't ruin the second cake. It just needed a little more time to set its structure.
Yes, and the critical thing about the slower oven is that the cake still successfully rose. A day 6 blastocyst has still successfully completed the journey.
It just took a little longer.
It has still compacted, cavitated, and differentiated. It just took 24 hours longer to build the house.
Do we know why it takes longer sometimes?
Sometimes it's just natural variation. Perhaps it took an extra few hours to repair a tiny transcription error before moving forward, which is actually a sign of a healthy cellular repair mechanism.
Oh, wow. So being slow could actually mean it was fixing itself.
Exactly.
Yeah.
We must deliberately tear down the myth that a day 6 blastocyst is inherently bad compared to a day 5.
That is so comforting to hear.
In fact, if you perform PGT and find that a day 6 embryo is chromosomally normal, its chances of resulting in a live birth are excellent, often approaching the success rates of a normal day 5.
What about day 7? Keeping the embryos in culture for a full week is a practice that really only became widespread in the last several years.
Day 7 blastocysts are less common, and they are generally viewed more cautiously by clinicians.
Because that's a pretty long delay.
It is. They represent a much later developing subgroup, and their overall implantation rates are statistically lower than day 5 or day 6 embryos.
But they aren't discarded automatically.
No, not at all. They can still be viable. If an embryo is robust enough to eventually form a blastocyst, even if it takes 7 days, it still has potential.
Right.
If a day 7 is the only blastocyst a patient has, or if it tests chromosomally normal, it absolutely offers a chance at pregnancy. We just set expectations accordingly.
So how does a lab balance this? How do you weigh the visual grade against the ticking clock?
It's the classic dilemma.
If you have a stunning textbook perfect 4-8A that didn't reach that stage until day 6, and a somewhat average-looking 3BBE that got there fast on day 5, which one do you pick? The beautiful late bloomer or the average early bird?
That highlights exactly how complex this process is. Generally speaking, many clinics will prioritize a top-quality day 6 over a mediocre day 5.
Really? The grade beats the clock.
Often, yes. The pristine morphology of the 4AA, the strong astronaut, and the flawless heat shield often outweighs the slight delay in the clock. Timing is informative, but it is just one variable within a much bigger picture.
It is incredible how much weight we put on this specific stage. The grades, the timing, the cellular differentiation.
It's the cornerstone of our work.
But I think it's really important to recognize that this deep reliance on blastocyst culture wasn't always the norm. This is a relatively modern paradigm shift. Let's give the listeners some historical context. Why did extended culture to the blastocyst stage completely change the landscape of IVF?
To understand the impact, we have to look back. In the early decades of IVF, the 1980s and 1990s, we routinely transferred embryos on day 2 or day 3, the cleavage stage.
We were transferring those early piles of bricks.
Exactly. Why? Because the laboratory culture media, the liquid nutrient solution the embryos live in, wasn't sophisticated enough to support the embryo's changing metabolic needs for 5 or 6 days.
It was essentially starvation after day 3.
It was a static solution, but an embryo's needs changed drastically. A day 3 embryo relies primarily on pyruvate for energy. A day 5 blastocyst relies heavily on glucose.
Oh, I see.
Because early labs couldn't provide this shifting diet, the lab was a relatively harsh environment. So the prevailing philosophy was, the safest place for the embryo is back inside the mother's uterus as quickly as possible.
But the problem with that philosophy is information, right?
We had almost none.
We talked about the maternal zygotic transition earlier. A day 3 embryo hasn't turned on its own genome yet. It hasn't proven it can build the house.
Exactly. We were transferring embryos essentially blind to their true structural potential.
Just guessing based on cell counts?
We would look at 4 nice-looking day 3 embryos, transfer all 4 of them in hopes that one would stick, and cross our fingers.
Wow.
This lack of selection capability led to 2 massive problems: lower overall success rates per transfer and a shockingly high rate of dangerous multiple pregnancies. Twins, triplets, or more, because we were putting so many embryos back at once.
So what changed? How do we get from transferring 4 day 3 embryos to transferring a single day 5 blastocyst?
The science of the culture media evolved. Scientists developed sequential media, fluids that we change out midway through the week, or modern single-step media that dynamically respond to the embryo's metabolism.
So the food got better.
Much better. We learned how to perfectly mimic the changing fluids of the female reproductive tract, providing pyruvate early on and glucose later.
Fascinating.
Once we could safely keep them in the lab longer, the entire field experienced a paradigm shift. Extended culture allowed for what we call developmental self-selection.
Developmental self-selection. That goes back to the great filter we talked about at the beginning.
Yes, exactly.
By waiting until day 5, the embryos that were genetically or metabolically incapable of forming a blastocyst naturally arrested in the dish.
They revealed their inability to progress. And by weeding out those embryos in the lab rather than inside the patient, we dramatically refined our embryo selection.
We stopped transferring embryos that never had a chance.
Right. We could finally identify the 1 or 2 embryos that actually had the architecture required to make a baby. This shift enabled the widespread adoption of single embryo transfer, or SET.
Which is much safer.
So much safer. We could confidently transfer just 1 beautiful blastocyst, knowing it had a high chance of success, thereby almost eliminating the massive medical risks associated with high-order multiple pregnancies.
Plus, there's a biological alignment factor, right?
What do you mean?
Like if this were happening naturally in a human body, a day 3 embryo is still traveling down the fallopian tube. It doesn't actually enter the uterus until day 5 or day 6, when it is a blastocyst.
Oh, yes, exactly. Transferring a day 5 blastocyst aligns the embryo transfer much more closely with the natural window of uterine receptivity. We are putting the right stage of embryo into the right environment at the right time.
But I want to ask a tough question here, on behalf of the patients listening who might have experienced a cycle where none of their embryos made it to day 5.
It's a heartbreaking situation.
It really is.
Yeah.
If more embryos arrest in the lab when we force them to wait until day 5, isn't there a risk that extended culture means we are losing embryos that might have survived if we had just put them back into the mother's body sooner?
That is such a common fear.
Is the lab environment, even a modern one, accidentally killing embryos that would have been babies?
That is a deeply emotional and very common fear. It is a question that haunted embryologists for years. But the overwhelming scientific consensus today is no.
Really?
No.
Yeah.
No, if an embryo arrests in a modern, high-quality IVF lab between day 3 and day 5, it is almost certainly because of intrinsic genetic or metabolic errors within the embryo itself, not because the lab failed.
An embryo itself was flawed.
Right. The uterus is not a magical incubator that can fix a broken genetic blueprint. If an embryo doesn't have the biological instructions to form a blastocyst in a perfectly controlled lab environment, it would not have formed a blastocyst in the uterus.
That is heavy.
It is. Extended culture is a necessary, albeit painful, developmental filter. It saves the patient the emotional and physical toll of transferring an embryo that was destined to miscarry or fail to implant.
That is a harsh truth, but a deeply necessary one to understand. The lab is simply revealing what biology has already determined.
Exactly.
But while Blastocyst culture gives us these incredible tools for selection, we must admit that it is not flawless. We have spent this entire deep dive marveling at the architecture, the grades, the timing, but we have to look at what can go wrong, and more importantly, what the microscope absolutely cannot see.
This is where we need to introduce a healthy dose of scientific humility.
Humility is always good in science.
Morphology, what the embryo looks like, is incredibly useful. But it is just shadows and shapes. When things don't look perfect, we see a wide range of suboptimal findings.
Like what?
We see delayed blastulation, where an embryo takes 7 or 8 days. We see poor expansion, where the cavity barely forms.
So the house is tiny.
Right. We see sparse inner cell masses that look like a faint dusting of cells rather than a tight ball. We see thin, uneven trophectoderms with large gaps where the tight junctions failed to form properly.
The heat shield is cracked.
Exactly. Sometimes we see partial collapse, where the fluid suddenly leaks out and the embryo shrinks back down. Or we see embryos that remain as morulae forever, unable to execute the cavitation process at all.
And when you see those things, the grades drop. The 4AAs become 2 BCs or 1 CCs. But what is the crucial nuance here? What are the absolute limits of this visual grading system?
The absolute limit of morphology is that it is the cover of the book, not the story inside.
The cover of the book.
Morphology helps us rank embryos and prioritize which one to transfer first. But it absolutely cannot guarantee chromosomal normality, it cannot guarantee implantation, and it cannot guarantee a live birth.
Let's tackle some remaining myths directly, because I think they are so prevalent in the patient community.
Let's do it.
Myth number 1, any blastocyst is a guaranteed success. If it made it through the great filter, it's a baby.
The reality is that reaching the blastocyst stage makes it a strong candidate, but it is not a guarantee. Even beautifully expanded blastocysts can fail to implant due to invisible genetic errors or issues with the uterine environment.
Right. Myth number 2, grading is a crystal ball. A 4AA will definitely work, and a 3BC will definitely fail.
The reality is that grading is a prioritization tool based on statistics. A 4AA statistically has a higher chance of implanting than a 3BC.
Across thousands of people.
Exactly, across a population of thousands. But for an individual patient, a lower grade blastocyst can, and very frequently does, result in a perfectly healthy live birth.
That's amazing.
Conversely, we see flawless, top-graded blastocysts fail to implant every single day.
Which is heartbreaking, but why? Why does a perfect-looking embryo fail?
Most often, it is because of what the microscope cannot see.
Aneuploidy?
Aneuploidy. An embryo can have the wrong number of chromosomes, too many or too few. Or it can be a mosaic embryo, meaning some cells have normal genetics and some have abnormal genetics.
So the blueprint itself is flawed.
Yes. An embryo can have these profound genetic errors and still manage to build a beautiful house. The cells can be genetically chaotic, yet still capable of pumping fluid and forming a tight cluster.
The pumps still work, even if the DNA is wrong.
Exactly. The microscope is entirely blind to the DNA.
If you are listening to this right now, and you have been through this process, you know the profound emotional roller coaster this causes.
It's agonizing.
You get the grading report from the embryologist, and you see that 4AA, and your heart soars. You feel like you have a perfect embryo. Or you get the report and see a 3BC or a day 6-4 BB, and you spiral into despair, convinced it is hopeless.
We see that emotional toll every day.
But we have to remember what we're talking about today. What we see on the outside, what the embryologist can grade under the light of a microscope, is just the physical structure. It is the bricks and the mortar. It is not the genetic story written on the pages inside. A fair-looking embryo might have perfect genetics and become a beautiful child, while a perfect-looking embryo might be carrying a genetic error that makes life impossible. We are making our best educated guess based on shadows.
That is exactly the reality of our field. We are using the best visual tools we have developed over 40 years, but they remain visual tools. Blastocyst grading improves our prioritization, but it does not and cannot eliminate uncertainty.
So let's slowly bring this all together. Let's recap this incredible journey we have taken today.
It's been a long road from the cleavage stage.
It really has. We started by watching a loose cluster of cells huddle together, zipping their membranes tight with E-catenin to form the solid morula.
Right, the team huddle.
We watched them fire up their mitochondria, actively pump sodium, and pull in fluid, carving out that internal cavity during cavitation to become a blastocyst.
Such a violent, active process.
We watched the embryo stretch and expand against its protective shell, eventually digesting its own way out. We marveled at the divergence of the cells, the inner cell mass destined to become the astronaut, the fetus, and the trophectoderm destined to become the heat shield, the placenta.
Two completely different destinies.
We navigated the complex cipher of the grading systems, learning that the numbers and letters are just a structured way to describe this architecture. And we explored the ticking clock, why a fast day 5 is ideal, but why a steady day 6 cake is still a beautiful, highly capable creation crossing the finish line.
We really have covered the very foundation of modern embryo selection. Reaching this stage is a monumental achievement for the biology in that petri dish.
It's a miracle of biology, honestly. But as we close, I want to leave you with a provocative thought. We have spent this entire deep dive talking about snapshots.
Snapshots, exactly.
The embryologist pulls the dish out of the incubator at 8:04 a.m. on day 5, looks down the microscope, takes a snapshot of the architecture, assigns a grade of 4AB, and puts it back. By the blastocyst stage, the embryo has revealed a great deal about its structure in that single snapshot.
But what if a single snapshot isn't enough?
Right.
What if the secret to truly understanding an embryo's competence isn't just what it looks like at exactly 8:63 a.m. on day 5, but how it behaved every single minute leading up to that point?
What if we didn't have to look away?
What if we could see exactly how long the compaction took? What if we could watch the cavity form in real time or catch a brief collapse and re-expansion that a single snapshot would completely miss?
That is the frontier.
Yeah.
And that is exactly where we're heading next. Thank you sincerely for joining us on this slow, deliberate deep dive today. We hope it brought clarity to one of the most mysterious and crucial stages of the IVF journey. We look forward to having you with us next time for our 11th deep dive, time-lapse imaging.
It's going to be fascinating.
We're going to move away from static snapshots and explore the incredible world of continuous observation, morphokinetics, and the promise and the controversy of watching human development unfold minute by minute. Until then, take care.